Imagine yourself floating in the deepest and most silent of spaces, where there is no wind, no sound, no horizon. Around you, only the infinite darkness, broken by countless points of light, twinkling in the distance, as if they were cosmic beacons indicating unknown routes. At the center of this vastness shines a star that appears ordinary to the eyes of any experienced astronomer, but is absolutely vital to us: the sun. It is the pulsing heart of everything we know, the source of light and heat that sustains every ocean, every leaf and every breath on the planet we call home. The solar system is, before any astronomical concept, the stage where our entire history has unfolded, from the first molecules that came together to form life to the civilizations capable of looking up and asking how it all began. When we speak of the solar system, we are referring to an incredibly complex and dynamic structure, composed of planets, moons, asteroids, comets, cosmic dust, and gases, all dancing in a balance dictated by gravitational forces. This dance is not static. It changes over millions and billions of years, shaped by collisions, gravitational interactions, and internal processes that sculpt surfaces and atmospheres. To understand the solar system, it is not enough to list its components. We must understand its origin, its evolution, and the fate that awaits it. And for that, we have to look far beyond what our eyes can see, diving into the history written in craters, rings, storms, and frozen rocks that carry secrets older than Earth itself. Since ancient times, humans have observed the sky with curiosity and awe. Ancient civilizations, such as the Babylonians, Egyptians, and Mayans, recorded the movements of celestial bodies, recognizing patterns and trying to decipher their influence on life on Earth. The sun and moon were seen as gods, and the planets, which moved differently from the fixed stars, were interpreted as divine messengers. This mythical view persisted for centuries until, with the advancement of observation and scientific thought, we began to uncover the physical nature of what we were seeing. Yet even with all modern knowledge, the solar system still holds mysteries capable of surprising us, and part of its magic lies in the fact that we will never exhaust all it has to reveal. The scale of the solar system defies human comprehension. When we think of the distances between the planets and the sun, the numbers become so large that they are almost abstract. Sunlight, which travels at an astonishing 300,000 kilometers per second, takes just over 8 minutes to reach Earth, but needs more than 4 hours to reach the edge of Neptune's orbit. And beyond Neptune lies a vast realm of icy bodies that stretches across almost unimaginable distances, such as the Kuiper Belt and the Oort cloud, the latter thousands of times farther from the sun than our planet. To put it into perspective, if the sun were the size of a soccer ball placed in the center of a field, Earth would be about 25 meters away, and Pluto, at the farthest point of its orbit, would be more than 1.5 kilometers away. Another fascinating aspect of the solar system is the dynamic balance that keeps it together. The sun's gravity is the central force that holds all planets and smaller bodies in orbit, but each planet also exerts influence on the others, causing small variations and disturbances that can have significant consequences over time. This balance is the product of billions of years of adjustments, where collisions, gravitational captures, and orbital migrations shaped the scene we see today. For example, it is believed that in the early stages of formation, gas giants such as Jupiter and Saturn migrated from their original positions, radically altering the fate of countless smaller bodies and even influencing the amount of material available to form rocky planets like Earth. The study of the solar system is not merely a scientific curiosity, it is fundamental to understanding Earth itself and the life it sustains. By observing other planets and moons, we can understand geological and atmospheric processes that also occur on our planet. By studying asteroids and comets, we gain clues about the chemistry and conditions that existed at the time of the sun and planet's formation. And by investigating the future of our stellar system, we can foresee the challenges our species may face on timescales far beyond any human calendar. Throughout this script, we will go through this history in detail, exploring from the primordial dust that gave rise to everything to the possible ways the solar system might one day disappear. We will visit each planet, dive into the unique characteristics of their moons, crossbelts of rock and ice, follow the luminous tails of comets, and venture to the invisible frontiers where the sun's influence blends with that of interstellar space. It will be a long and fascinating journey, guided by the human desire to understand our place in the cosmos and filled with discoveries that continue to shape our knowledge and awaken our sense of wonder. Our starting point is simple yet profound. The solar system is our cosmic address. Everything we know, everything we love, and everything we study is, in some way, connected to this harmonious set of celestial bodies. And understanding this stellar home is both an act of curiosity and an act of survival. To understand how the solar system was born, we must imagine a time so distant that it precedes the very existence of Earth, the Moon, the Sun, and even the particles that now make up each planet. About 4,600,000,000 years ago, our region of the galaxy was nothing more than a point within an immense interstellar cloud, composed mainly of hydrogen, helium, and small amounts of heavier elements. This cloud, called a molecular nebula, floated in space like a cold, dark mass, with denser regions and others more rarefied. It was essentially a cosmic reservoir of raw material that, under certain conditions, could give rise to stars and planetary systems. The trigger that began transforming this cloud into something much greater is still a subject of debate among scientists, but one of the most accepted hypotheses suggests that a nearby supernova explosion, the collapse and death of a massive star, sent a shockwave through this cloud, compressing it and causing internal regions to become denser and unstable. These regions, under the effect of gravity, began collapsing in on themselves. The collapse was not uniform. As matter fell toward the center, the natural rotation of the cloud caused it to flatten, forming a rotating disk with a concentration of mass at its core. This dense and hot core, under immense gravitational pressure, became the embryo of our Sun. The formation of the Sun was accompanied by chaotic events in the rest of the disk. Particles of dust and ice began to collide, initially sticking together in a fragile way, forming small aggregates known as planetesimals. These bodies, through repeated collisions, grew in size and became protoplanets. In the inner part of the disk, closer to the newborn Sun, the intense heat prevented the condensation of volatile elements such as water and methane, allowing the formation of rocky planets, Mercury, Venus, Earth, and Mars. In the more distant regions, where cold-dominated ice and gases accumulated in large quantities, enabling giant planets like Jupiter and Saturn to grow rapidly, attracting massive hydrogen and helium atmospheres. This formation model is known as the solar nebula hypothesis, and although it is widely accepted, it is not free from adjustments and refinements. New discoveries suggest that in the first few million years, the gas giants migrated from their original positions, profoundly altering the architecture of the solar system. Models such as the NICE model propose that Jupiter and Saturn shifted, scattering comets and asteroids, and triggering the so-called late heavy bombardment, a period of frequent impacts that shaped the surfaces of planets and moons. The birth of the solar system was a process of intense transformation, but also of delicate balance. Gravity united matter, but collisions and the intense radiation of the young Sun constantly reshaped the disk. The inner regions became environments of scorching heat, while the outermost edges remained cold and filled with ice. Between these extremes, intermediate zones, like the one that gave rise to Earth, gathered the ideal conditions for the formation of a planet capable of harboring liquid water and, eventually, life. The formation of the Sun itself was a spectacle of physics and energy. As matter accumulated in the core, pressure and temperature increased until they reached the critical point for nuclear fusion to begin. When this occurred, hydrogen began transforming into helium, releasing colossal amounts of energy. The Sun shone for the first time, its radiation sweeping across the disk and dissipating some of the lighter material, helping to end the accretion phase of planets in the inner regions. Meanwhile, smaller bodies like asteroids and comets remained as leftover fragments of this process, functioning as cosmic time capsules, preserving the chemical composition of the original nebula. This is why the study of these small bodies is so valuable. They carry chemical and isotopic signatures that reveal details about the infancy of the solar system. Space missions, such as those that have brought back asteroid samples, are comparable to opening safes sealed for billions of years, containing clues about the earliest chapters of our stellar history. This origin was not an isolated event. Across the galaxy, clouds of gas and dust continue to collapse to form new planetary systems. By studying the birth of our own solar system, we can see a repeating pattern, but we also understand that small variations in the initial conditions can generate completely different worlds. This perspective is crucial for modern astronomy, as it helps us predict which systems out there might harbor Earth-like planets and perhaps life. What began as a cold and silent cloud transformed into a vibrant system, with a shining sun at its center and a diversity of worlds orbiting around it. The story that followed, full of impacts, migrations, and cosmic climate changes, shaped what we know today and left clues that allow us to reconstruct each stage of this process. If the birth of the solar system was marked by a delicate balance between gravity and motion, its infancy was anything but peaceful. Shortly after the formation of the Sun and the first embryonic planets, the scene was one of constant chaos, where collisions, impacts, and migrations shaped every detail of planetary architecture. Imagine a vast, rotating disk filled with rock, ice, dust, and gas, with billions of bodies of different sizes moving in unstable trajectories. This was the environment during the first hundreds of millions of years, a cosmic battlefield in which forming worlds grew through an endless sequence of violent encounters. The young, incomplete protoplanets increased in size through accretion, the process by which smaller objects collide and merge with larger bodies, adding their mass and energy. In every collision there was heat, fusion of materials, and often the ejection of fragments that returned to the disk to participate in new interactions. This cycle was so intense that during this early period, no planet had a stable surface. Everything was in constant transformation, with seas of lava, temporary atmospheres, and impacts that could completely reshape geography in a matter of hours. Between 4.1 and 3.8 billion years ago, an event occurred that is recorded as one of the most destructive periods in the history of the solar system, the Late Heavy Bombardment. This name describes a phase in which an extraordinary number of asteroids and comets collided with planets and moons, leaving deep and lasting scars. Evidence of this period can still be seen in the craters of the Moon, Mercury, and many moons of Jupiter and Saturn. One of the most accepted hypotheses to explain this phenomenon involves a gravitational reorganization of the giant planets, especially Jupiter and Saturn, which would have sent a rain of debris toward the inner solar system. This event not only sculpted the surfaces of worlds, but may also have played a crucial role in delivering water and organic compounds to Earth. It was during this turbulent period that one of the most significant impacts in our planet's history is believed to have occurred: the collision between the primitive Earth and a Mars-sized body, referred to by some scientists as Theia. The impact was so violent that part of Earth's mantle and material from Theia was ejected, forming a ring of debris around Earth. Over time, this material coalesced and gave birth to our Moon. This theory, known as the giant impact hypothesis, not only explains the Moon's composition and orbit, but also helps us understand the tilt of Earth's axis and the climate stability that made the evolution of life possible. The impacts of this era were not mere accidents. They were fundamental construction mechanisms. Giant collisions helped differentiate planets, separating metallic cores from rocky outer layers and contributing to the formation of initial atmospheres. Some worlds were destroyed and reabsorbed into the disk, while others grew enough to become stable bodies. The energy released in these encounters shaped surface chemistry, heated subsurface oceans, and in some cases, completely sterilized planets that might have been beginning to develop conditions for life. Another important factor in this violent youth was planetary migration. Studies suggest that Jupiter, the largest planet in the solar system, may have moved closer to the Sun before retreating to its current position. This displacement would have swept away vast amounts of debris, altering the orbits of other planets and directly influencing the distribution of asteroids and comets. This gravitational dance helped define the current boundaries of the asteroid belt and preserve certain regions, such as the so-called habitable zone, where Earth resides. During this phase, the diversity of worlds began to consolidate. Rocky planets near the Sun developed solid surfaces and thin or non-existent atmospheres, while gas and ice giants in the outer regions accumulated immense layers of gases, becoming colossal bodies with dozens of moons and complex ring systems. Smaller bodies, such as asteroids and comets, remained as frozen witnesses of this era, preserving materials virtually unchanged since the original formation. It is important to understand that, on a cosmic scale, these millions of years of chaos were a natural and necessary stage. Without the collisions and migrations of this early period, the solar system might have followed a completely different configuration, perhaps without the Earth as we know it, or without the ideal conditions for life to emerge. Each impact, no matter how destructive it may seem, contributed to the final harmony that sustains the dance of the planets around the Sun. This period of extreme violence, therefore, should not be seen solely as destruction, but as a creative process in which energy and matter were redistributed to shape the system we know today. And although giant collisions have become rare in modern times, the legacy of this turbulent childhood remains written in the craters, rings, and orbits we observe. The Sun, now seen as a stable and bright sphere in the sky, had a dramatic and turbulent beginning. To understand the early evolution of this star, we must picture the moment when it was still nothing more than a dense, hot core at the center of the protoplanetary disk, formed by the gravitational collapse of the solar nebula. This core, fed by the constant infall of matter, was wrapped in a thick layer of dust and gas, and emitted energy not through nuclear fusion, as it does today, but simply by contracting under its own weight, converting gravitational energy into heat. This stage is known as a protostar, and during it the Sun was still far from the stability it has now. During this initial phase, the protostar experienced a delicate balance. Gravity tried to compress it ever more tightly, while internal pressure, caused by the progressive heating of the core, tried to expand it. The disk around it continued to feed this young star with material, while at the same time, initial stellar winds began to blow outward, sweeping away some of the dust and gas. Observations of protostars in other regions of the galaxy give us clues about how this stage of the Sun unfolded, showing that these winds and jets of particles are capable of shaping the disk and directly influencing the formation of planets. The turning point in the Sun's evolution came when the temperature in its core reached approximately 15 million degrees Celsius. At this extreme temperature, the conditions for nuclear fusion were met, and hydrogen atoms began fusing to form helium. This process released a colossal amount of energy, marking the official beginning of the main sequence phase. It was at this moment that the Sun fully lit up, beginning to emit sustained light and heat, powered by fusion, a process that has kept our star stable for billions of years since. With the onset of fusion, radiation pressure became sufficient to counterbalance gravity, stabilizing the Sun. This stability was essential for the formation and maintenance of the planets, as it reduced the extreme variations in brightness that characterize earlier stages of stars. The protoplanetary disk, still present, began to dissipate rapidly, partly due to intense radiation and now much stronger solar wind. This solar wind played a crucial role. It swept away much of the remaining gas in the inner regions of the solar system, preventing the rocky planets from accumulating atmospheres as thick as those of the gas giants. In the first millions of years of this stable phase, the Sun rotated faster than it does today and exhibited intense magnetic activity with solar flares and coronal mass ejections that were much more frequent and energetic. This tempestuous youth left its mark across the solar system. For example, the intense ultraviolet radiation emitted during this time contributed to the early evolution of planetary atmospheres, altering chemical compositions and even removing gases from worlds with less protection. Mercury and Mars, for instance, suffered significant atmospheric losses due to the combined effects of radiation and solar wind. This initial phase also coincided with the end of the great period of bombardment that shaped the surfaces of planets and moons. The stabilization of solar luminosity was a decisive step in allowing regions like Earth to maintain temperatures compatible with the presence of liquid water. It is important to remember that the Sun's brightness was not the same from the start. In the past, it was about 30% less luminous than it is today, a phenomenon known as the faint young sun paradox. Despite this, it is believed that the combination of greenhouse gases and Earth's geological characteristics allowed our planet to remain warm enough to sustain liquid oceans and eventually life. The Sun's transition from an unstable protostar to a mature star marked the beginning of a relatively calm era in the solar system. This relative calm, of course, does not mean the absence of significant events. but rather the creation of a much more predictable environment, favorable to orbital and climatic stability. From this point onward, the Sun followed an evolutionary path that, according to stellar models, will keep it in the main sequence for about 10 billion years in total, currently being around halfway through that journey. This early evolution not only defined the conditions for the formation and development of planets, but also set the limits for where life could arise. The Sun's stable and constant radiation is, to this day, the driving force that fuels ecosystems and sustains Earth's delicate climatic balance. That is why when we study the Sun's youth, we are not merely revisiting an ancient chapter of cosmic history, but understanding the foundation of everything that made life on our planet possible. The Sun, often reduced in popular imagination to a simple ball of fire in the sky, is in fact an extraordinarily complex thermonuclear power plant whose stability and behavior determine not only the fate of Earth, but of the entire solar system. It is classified as a yellow dwarf star of spectral type G2V, and its mass accounts for about 99.86% of all the mass in the system. This colossal concentration of matter exerts a gravity strong enough to keep all planets, moons, asteroids, and comets in their orbits, and the energy it produces is the main source of light and heat that sustains life on our planet. The Sun's structure is divided into distinct layers, each with specific functions and characteristics. At the center is the core, where nuclear fusion reactions occur. Here the temperature reaches about 15 million degrees Celsius, and the pressure is so intense that hydrogen atoms overcome their natural electrical repulsion and fuse to form helium. This fusion releases energy in the form of photons and subatomic particles. However, this energy does not reach the surface immediately. It takes thousands or even millions of years to pass through the radiative zone, where energy is transferred slowly by radiation. It then enters the convective zone, where movements of hot plasma transport heat more quickly to the visible surface. The apparent surface of the Sun, called the photosphere, is the layer from which sunlight escapes into space. It is here that we observe phenomena such as sunspots, regions that are temporarily cooler and darker, associated with intense magnetic fields. Above the photosphere lies the chromosphere, a thinner layer that appears in reddish tones during solar eclipses. Higher still is the solar corona, the Sun's outer atmosphere, which extends millions of kilometers into space and reaches surprisingly high temperatures, up to millions of degrees Celsius, a phenomenon that still defies complete explanation in solar physics. The Sun's central mechanism is nuclear fusion through the proton-proton chain, in which 4 hydrogen nuclei combine to form a helium nucleus, releasing energy in the form of electromagnetic radiation and particles such as neutrinos. This energy propagates through space, and upon reaching Earth is absorbed by oceans, continents, and the atmosphere, powering everything from plant photosynthesis to global weather patterns. Without the stability of this process, maintaining Earth's thermal balance would be impossible. In addition to continuous energy production, the Sun exhibits magnetic activity cycles that influence the entire solar system. The most well-known is the approximately 11-year solar cycle, during which the number of sunspots, flares, and coronal mass ejections rises and falls. In periods of high activity, the Sun emits more radiation and charged particles, which can directly affect satellites, communication systems, power grids, and even generate spectacular polar auroras. This magnetic behavior is also linked to the periodic reversal of the Sun's magnetic poles, a phenomenon that, while not catastrophic to life on Earth, demonstrates the dynamic and living nature of our star. The Sun not only heats and illuminates, but also protects the solar system. The solar wind, a continuous flow of charged particles it emits, creates a vast bubble called the heliosphere, which extends far beyond Pluto's orbit. This heliosphere acts as a shield against much of the high-energy cosmic radiation coming from other regions of the galaxy, making the space environment within the solar system relatively less hostile for probes, astronauts, and even for the development of life on planets like Earth. The Sun's importance for all planets is immeasurable. It regulates temperatures, defines habitable zones, and influences space weather that affects bodies and atmospheres. In Earth's case, its energy maintains water in liquid form, an essential condition for life. On Mars, being near the edge of the habitable zone and having lost much of its atmosphere, Solar radiation drastically altered its environment. In the gas giants, sunlight and heat, even weakened by distance, still play a role in atmospheric dynamics and the formation of monumental storms. By studying the Sun in detail, we are not merely observing the closest star. We are looking at the beating heart of our system, whose lifespan and behavior will inevitably determine the fate of all the worlds orbiting it. It is, at the same time, a symbol of stability and a reminder that even stars have finite life cycles, with a beginning, a peak, and an inevitable end. The rocky planets, also known as terrestrial planets, are those formed predominantly by solid materials such as silicates and metals. In the solar system, this category includes Mercury, Venus, Earth, and Mars, located closer to the Sun in the so-called inner region of the system. Despite having unique characteristics, they all share a basic structure made up of an iron metallic core, rocky mantle, and a solid crust, as well as having defined surfaces and, at some point in their history, having undergone active geological processes. Their main similarity lies in their dense composition, the result of forming in a region where temperatures were too high for light gases and ice to condense. During the solar system's formation, the intense radiation of the young Sun swept away most of the volatile elements from this region, leaving behind heavier materials that fuse to form solid worlds. This composition ensures a high average density, generally above 3,000 kg, and surfaces capable of recording impacts, volcanism, erosion, and tectonic movements. Another common feature is the presence of differentiated internal layers. The core, composed mainly of iron and nickel, is responsible for generating, in some cases, magnetic fields when combined with convection movements and planetary rotation. The mantle, rich in silicates, is the intermediate layer that conducts heat from the interior to the surface, influencing volcanism and tectonics. Finally, the crust is the outermost layer, where landscapes, mountains, valleys, and craters are found. Although all have this general structure, the thickness and composition of these layers vary from planet to planet, directly influencing their geological and atmospheric characteristics. The rocky planets also share exposure to asteroid and comet impacts throughout their history. The lack of dense atmospheres in some of them, such as Mercury, has allowed craters billions of years old to remain almost unchanged. Planets with thicker atmospheres, such as Venus and Earth, have had their surfaces reshaped by erosion, volcanism, and climatic processes, erasing some of these ancient marks. Despite their similarities, the differences between them are striking. Mercury, for example, is small, extremely dense, and almost without an atmosphere, leading to brutal temperature variations between day and night. Venus, in contrast, is enveloped by a thick carbon dioxide atmosphere, with a greenhouse effect so intense that surface temperatures are high enough to melt lead. Earth stands out for its abundance of liquid water and oxygen-rich atmosphere, which sustains life. Mars, meanwhile, has a thin atmosphere, evidence of rivers and lakes in the past, and polar caps made of water ice and carbon dioxide. Surface gravity on these planets varies considerably, influencing not only atmospheric retention, but also the height of mountains and the extent of valleys. Mars, with lower gravity than Earth, is home to Olympus Mons, the largest known volcano in the solar system. Venus, despite being similar in size to Earth, features terrain marked by vast plains and volcanic structures that indicate geological activity in the past, and possibly even in the present. Another point of contrast is the presence or absence of a giant global magnetic field. Earth maintains a strong magnetic field generated by the movement of liquid iron in its core, which protects the surface from solar and cosmic radiation. Mercury has a weak magnetic field, while Mars and Venus currently lack a significant protective shield, which contributed to the loss of much of their atmospheres over time. Temperature is also a decisive factor in the conditions of each planet. Proximity to the Sun makes Mercury and Venus scorching worlds, while Mars, farther away, experiences extremely low temperatures. Earth occupies a privileged position in the habitable zone, where water can remain liquid on the surface, favoring the emergence and maintenance of life. Studying the rocky planets is not only about understanding distant worlds, but also about revisiting Earth's own history. They represent different chapters of the same cosmic book, revealing how variables such as size, distance from the Sun, internal composition, and the presence of an atmosphere can create radically different environments from a similar origin. They are natural laboratories that clearly show how a planet's destiny is shaped by its formation and evolution. Mercury is the smallest and innermost planet of the solar system, orbiting the Sun at an average distance of only 58 million kilometers. Being so close to our star, it completes an orbit in just 88 Earth days, but curiously takes 59 days to rotate once on its own axis. This rhythm of rotation and revolution creates a peculiar phenomenon. A solar day on Mercury, the time between one sunrise and the next, lasts the equivalent of 176 Earth days. This means that if someone could walk on its surface, they would see the sun rise very slowly, remain in the sky for weeks, and then set just as gradually. Its geological history is marked by impacts and intense volcanic activity in the past. Mercury's surface is covered with craters of all sizes, some so large that they stretch for hundreds of kilometers, such as the Caloris Basin, which is more than 1,500 kilometers in diameter. This basin was formed by a colossal impact about 3.9 billion years ago and is surrounded by mountains and rippled terrain created by the energy released in the collision. In addition, there are vast plains formed by ancient lava flows, indicating that the planet underwent periods of volcanism billions of years ago, when its interior was still hotter and more active. One of the most intriguing characteristics of Mercury is its high density. Considering its small size, it is surprisingly heavy, indicating that it has a huge metallic core occupying about 85% of the planet's radius. This core is made mainly of iron and nickel, and surprisingly, is still partially liquid, which allows the generation of a magnetic field. Although this field is only about 1%, the intensity of Earth's magnetic field, its existence is unusual for such a small and old planet, suggesting that its core has retained internal heat for much longer than previously thought. Mercury's atmosphere, technically called an exosphere, is extremely thin, almost non-existent, composed of atoms of oxygen, sodium, potassium, and helium. It is so rarefied that particles are easily lost to space, constantly replaced by material released from the surface due to micrometeorite impacts and the action of the solar wind. This atmospheric fragility means that the planet cannot retain heat, causing extreme temperature variations. During the day, the surface can reach about 430 degrees Celsius, while at night it drops to an impressive 180 degrees Celsius. These harsh conditions make Mercury one of the most inhospitable environments in the solar system, but this does not diminish its scientific value. It is a natural record of the early history of the solar system, preserving marks and structures that have been erased on other planets by geological or climatic processes. Studying it helps us understand not only the formation of rocky worlds, but also the thermal and magnetic evolution of small planetary bodies. Missions such as Mariner 10 in the 1970s and Messenger between 2011 and 2015 revealed detailed images and data of its surface, as well as surprising discoveries, such as the presence of water ice in permanently shadowed craters near the poles. Despite receiving intense solar radiation, these regions never see direct sunlight, allowing the ice to remain stable for billions of years. This discovery shows that even the planet closest to the Sun harbors elements we associate with much colder environments. Another curious aspect is that, due to its lack of a dense atmosphere, Mercury's sky is not blue like Earth's, but completely black, even during the day. This means that if we were on its surface, we could see the sun shining intensely and, at the same time, see the stars in the dark background of space. In addition, Mercury's proximity to the Sun causes it to experience an effect called perihelion precession, a slow rotation of the closest point of its orbit, which was precisely explained only by Albert Einstein's general theory of relativity, making it a natural laboratory for testing fundamental laws of physics. Mercury, with its combination of thermal extremes, unexpected magnetic field, and surface marked by ancient impacts, is a reminder that even the smallest planets can hold great stories. It is, in essence, a cosmic time capsule, a silent witness to the birth and early ages of the solar system. Venus, often called the Earth's twin, due to its similar size and composition, is in reality one of the most extreme and inhospitable worlds in the solar system. Its mass, diameter, and gravity are comparable to our planets, but the similarities practically end there. Enveloped by a dense, suffocating atmosphere composed of about 96% carbon dioxide and thick clouds of sulfuric acid, Venus hosts the most intense greenhouse effect known. This effect traps heat so efficiently that the average surface temperature reaches about 465 degrees Celsius, hotter than Mercury, even though it is almost twice as far from the Sun. This temperature is constant on both the day and night sides, a result of the atmosphere's ability to redistribute heat. Its surface, observed by radar from probes such as Magellan, reveals vast plains, mountain ranges, and an impressive number of volcanoes. There is evidence that many of these volcanoes may have been active in the relatively recent past, and possibly some are still active today. Venusian topography includes unique formations such as corona, gigantic circular structures formed by the upward movement of magma in the mantle, deforming the crust. The planet also has fewer impact craters than expected, suggesting that the surface was renewed by large-scale volcanic activity hundreds of millions of years ago. Venus's thick atmosphere not only traps heat, but also exerts a crushing pressure, about 92 times greater than Earth's at sea level. This is equivalent to the pressure found nearly a kilometer deep in Earth's oceans. Any probe attempting to land on the surface must endure not only this extreme pressure, but also intense heat and the corrosive action of acidic compounds. Soviet Venera missions in the 1970s and early 1980s managed to land and transmit data for a few minutes before succumbing to these brutal conditions. Another fascinating aspect of Venus is its retrograde and extremely slow rotation. It spins in the opposite direction to most planets, taking 243 Earth days to complete one rotation, but only 225 days to orbit the Sun. This means that a day on Venus is longer than its year, and that the Sun, seen from its surface, would rise in the west and set in the east. This unusual rotation remains the subject of study, with hypotheses ranging from large past impacts to gravitational interactions with the Sun and other planets. Above the thick clouds, winds in Venus's upper atmosphere reach speeds exceeding 350 km/h, circling the planet in just 4 Earth days. This atmospheric superrotation contrasts with the planet's slow rotation, and its origin remains a mystery to scientists. Additionally, the clouds reflect much of the sunlight, making Venus one of the brightest objects in Earth's night sky, visible to the naked eye shortly after sunset or before sunrise, when it earns the nickname morning star or evening star. In recent years, Venus has regained scientific attention due to evidence of compounds potentially associated with life in its clouds, such as phosphine. In 2020, a study suggested the detection of this molecule in unexpected concentrations, sparking debates about its origin. Although there is no consensus yet, and alternative chemical hypotheses are possible, the idea has rekindled interest in future exploration missions. The environment in the clouds, about 50 to 60 kilometers in altitude, is much milder in temperature and pressure, raising the theoretical possibility of microbial life adapted to acidic conditions. Exploring Venus is essential not only to understand its history, but also to grasp the potential fate of Earth-like planets. The study of its runaway greenhouse effect serves as a warning about the role of atmospheres in climate regulation. Observing Venus teaches us that two planets with similar origins can evolve in radically different ways, shaped by small initial variations and internal processes that, over billions of years, amplify into extreme outcomes. Thus, Venus is both a distorted mirror of Earth and a natural laboratory for the study of atmospheres, planetary geology, and extreme climate. It is a reminder that in the vast catalogue of possible worlds, even close neighbors can follow radically different paths, creating landscapes and conditions that challenge even the most advanced space exploration missions. Earth is, as far as we know, the only planet in the universe that harbors life. Although this statement may seem simple, it is the result of an extremely rare and complex combination of astronomical, geological, chemical, and biological factors. Its history began about 4.54 billion years ago, when it formed from the same cloud of gas and dust that gave rise to the Sun and the other bodies in the solar system. In its first millions of years, young Earth was a hostile environment. Seas of lava covered much of the surface. The atmosphere was composed of volcanic gases, and constant impacts from asteroids and comets reshaped the terrain, bringing with them chemical elements and possibly water. It is believed that Earth's water came both from the melting of hydrated minerals within its interior and from the impact of ice-rich comets and asteroids. This water accumulated in primordial oceans, and it was in this liquid environment that the first complex organic molecules began to form. Before that, however, Earth experienced an event that would change its destiny forever: a collision with a Mars-sized body called Theia, about 4.5 billion years ago. This collision not only merged part of Theia with Earth, enriching the planet's core with metals, but also generated a disk of debris that would later coalesce to form the Moon. The Moon's presence is one of the most important factors in the stability of our planet. Its gravitational pull influences the tides and helps stabilize Earth's axial tilt, preventing abrupt climate changes over millions of years. This climatic stability was essential for life to emerge and evolve steadily. From a geological perspective, Earth is unique among the rocky planets in having active plate tectonics. The slow but constant movement of lithospheric plates recycles crustal material, regulates the amount of carbon dioxide in the atmosphere, and creates a variety of environments, such as mountain ranges, volcanoes, and ocean basins. This geological mechanism not only shapes the landscape but also acts as a natural thermostat, helping maintain the climate within life-compatible limits for billions of years. The current terrestrial atmosphere is composed mainly of nitrogen, 78%, and oxygen, 21%, with small amounts of other gases such as argon and carbon dioxide. However, it wasn't always like this. The primitive atmosphere was rich in carbon dioxide, methane, and ammonia, and contained no free oxygen. Oxygen began to accumulate about 2.4 billion years ago during the so-called Great Oxidation Event, caused by the photosynthesis of microorganisms such as cyanobacteria. This atmospheric transformation was a milestone, allowing for the emergence of more complex life forms and permanently shaping Earth's chemistry. The origin of life on Earth is one of science's greatest mysteries. The most accepted theories suggest that simple organic molecules formed spontaneously under specific conditions and, over millions of years, evolved into self-replicating structures. These first life forms, likely unicellular and microscopic, adapted to extreme environments such as submarine hydrothermal vents and mineral-rich lakes. Over time, diversity increased, with the emergence of photosynthetic organisms, then multicellular beings, and finally complex animals and plants. Another factor that makes Earth unique is its magnetic field. Generated by the movement of liquid iron in its outer core, this invisible shield protects the planet from solar and cosmic radiation by deflecting charged particles that could otherwise erode the atmosphere and harm life. This field, combined with the atmosphere and the ideal position in the so-called habitable zone, creates an environment where water remains liquid and temperatures stay relatively stable. Earth also exhibits an incredible diversity of ecosystems, ranging from arid deserts to lush tropical forests, from deep oceans to frozen polar regions. This variety results from a complex interaction between climate, terrain, chemistry, and life, which continuously feed back into a cycle of change and adaptation. Over billions of years, the planet has gone through ice ages, global warmings, mass extinctions, and recoveries, demonstrating remarkable resilience. Finally, the story of Earth is also the story of humanity. We are part of the final product of this long cosmic journey, and our very existence depends on the fragile balance that keeps the biosphere functioning. Understanding Earth's uniqueness is not just a scientific exercise, but also a reminder of the responsibility we have to preserve this rare environment in a vast and, as far as we know, mostly inhospitable universe. The Moon, our only natural satellite, is far more than just a bright spot in the night sky. It has been an inseparable companion to Earth since ancient times and plays a profound role in the geological, climatic, and biological history of our planet. It is estimated to have formed around 4.5 billion years ago, shortly after the colossal impact between the young Earth and a Mars-sized body called Theia. This collision ejected a massive amount of material into space, which became trapped in Earth's orbit and, over millions of years, clumped together to form the Moon. Evidence of this origin is recorded in the chemical composition of lunar soil, which is very similar to Earth's crust. though with subtle differences that reveal the violence of that primordial event. The Moon's presence has been essential for Earth's stability over billions of years. Its gravity directly influences the tilt of Earth's axis, keeping it relatively stable at about 23.5 degrees. Without this stability, Earth's climate could have undergone chaotic variations, making the development and maintenance of life much more difficult. Furthermore, the gravitational interaction between the Moon and Earth is responsible for ocean tides. Tides have not only shaped coastal ecosystems, but may also have played an important role in the emergence of life, creating intertidal zones where organic molecules were concentrated and exposed to cycles of drying and wetting, favoring complex chemical reactions. The lunar cycle is also one of the most striking phenomena in the Earth's sky. The Moon does not shine on its own. What we see is sunlight reflected off its surface. Its phases of new waxing, full and waning result from the changing angle between Earth, the Moon and the Sun over approximately 29.5 days. This cycle not only guided calendars for various ancient civilizations, but also influenced myths, beliefs, and even agricultural practices throughout human history. In many cultures, the Moon is a symbol of renewal and the passage of time. Geologically, the Moon is a fascinating world. Its surface is covered by lunar maria, vast basaltic plains formed by ancient lava flows, and highlands filled with impact craters, some billions of years old. The absence of a significant atmosphere means there is no erosion from wind or water, preserving traces of ancient events like cosmic fossils. Samples collected by Apollo missions revealed that the Moon once had volcanic activity, but is currently a geologically inactive body, although small moonquakes still occur due to gravitational adjustments with Earth. Another important aspect is tidal locking. The Moon takes the same amount of time to rotate on its axis as it does to orbit Earth, which is why it always shows the same face to us. This means that until space probes arrived, the so-called far side of the Moon was completely unknown. Today we know that this side has a more rugged surface and fewer maria, probably due to differences in the crust that formed shortly after its creation. Beyond its physical impact, the Moon also marked a milestone in the history of space exploration. In 1969, the Apollo 11 mission took the first humans to walk on its surface, opening an unprecedented chapter in the relationship between humanity and space. These achievements not only expanded our knowledge of the satellite, but also reinforced the view of Earth as a small and fragile blue dot in the vast cosmos. The Moon continues to be a major focus of scientific and strategic interest. Plans for lunar bases, resource exploitation, and using the satellite as a stepping stone for more distant missions are underway. Scientifically, studying it offers clues about the formation and evolution of the solar system, as well as serving as a natural laboratory for better understanding the effects of space radiation and microgravity. Ultimately, the Moon is much more than a nearby cosmic neighbor. It is a pillar in Earth's history, influencing tides, climate rotation, and possibly the very emergence of life. It is a constant reminder that our planet does not travel alone around the Sun, and that this partnership, born in fire and collision, continues to shape the world we inhabit. Mars, known as the Red Planet because of the iron oxide coating its surface, is the fourth planet from the Sun and one of the most studied worlds in the solar system. It holds a special fascination because it has characteristics that make it, in many respects, the most likely candidate to have hosted life in the past, and perhaps even in the present, in microscopic form. Its diameter is about half that of Earth, its gravity is only 38% of Earth's, and its climate is cold and dry, with average temperatures around -60 degrees Celsius, although they can range from -125 degrees Celsius in the polar regions in winter to slightly above zero near the equator during the day. The most intriguing aspect of Mars's history is the presence of liquid water in the past. Geological evidence obtained by probes and rovers shows ancient riverbeds, deltas, and minerals that form only in the presence of water. Orbital images reveal branching valleys and sedimentary deposits indicating that billions of years ago, Mars had a much wetter and warmer climate, with lakes and possibly even oceans covering vast areas. Today, liquid water on the surface is unstable due to low atmospheric pressure, but it still exists in the form of ice in the polar caps and in underground deposits detected by radar. The polar caps of Mars are composed of water ice and dry ice. frozen carbon dioxide, which expand and contract with the seasons. In winter, carbon dioxide from the atmosphere freezes, increasing the size of the caps, while in the Martian summer, part of it sublimates back into the atmosphere. These seasonal changes affect not only the appearance of the caps, but also the planet's atmospheric pressure. The Martian atmosphere is extremely thin, composed mainly of carbon dioxide, with traces of nitrogen and argon. This thinness, combined with the absence of a significant global magnetic field, leaves the surface exposed to solar and cosmic radiation, creating a hostile environment for life as we know it. However, the possibility of subsurface microbial life is still actively studied, as below the surface the environment could offer protection from radiation and more stable conditions. Missions such as the Curiosity rover and Perseverance have as one of their main objectives to search for signs of past life, collecting samples and analyzing the chemical composition of the soil. Geologically, Mars is a planet of extremes. It hosts Olympus Mons, the largest known volcano in the solar system, about 22 kilometers high and 600 kilometers in diameter, so large that its base covers an area equivalent to that of the state of Texas. It also has Valles Marineris, a gigantic canyon system stretching over 4,000 kilometers and reaching 7 kilometers deep, probably formed by tectonic and erosive processes. These impressive geographic landmarks reveal a past of intense volcanic and tectonic activity, although Mars is now considered largely geologically inactive on most of its surface. Human interest in Mars is not only scientific, but also exploratory and even colonizing. Its relative proximity to Earth and the presence of resources such as water ice make the planet a priority target for future manned missions. However, the challenges are immense. Low gravity, intense radiation, and global dust storms, which can engulf the entire planet and last for months, will require advanced technologies to ensure human survival. Mars has also been the target of orbital probes and landers from various space agencies, and continues to be constantly monitored. These missions have revealed not only scientific data, but also images that fuel popular imagination and theories about extraterrestrial life. Although there is no concrete evidence of living organisms, the possibility of finding microbial fossils or even active life in underground environments keeps Mars at the heart of modern astrobiology. Ultimately, Mars is a world that bears the scars of a more hospitable past, and for that reason offers us a glimpse of what can happen to Earth-like planets under different conditions. It is, at the same time, a natural laboratory for the study of planetary geology, atmospheric evolution, and the search for life, and a possible destination for humanity when we decide to expand our horizons beyond Earth. Between the orbits of Mars and Jupiter lies a vast region populated by millions of rocky bodies of different sizes, known as the asteroid belt. This area is not an empty space sprinkled with a few rocks, as often portrayed in science fiction. In reality, it is an enormous reservoir of primitive material left over from the formation of the solar system about 4.6 billion years ago. These bodies, called asteroids, are fragments that never merged to form a planet, largely due to the intense gravitational influence of Jupiter, which prevented the complete accretion of matter in this region. The diversity of asteroids is remarkable. They range from small rocks only a few meters in diameter to worlds hundreds of kilometers across. Their composition is also varied. There are metal-rich asteroids, type M, those composed mainly of silicate rocks, type S, and those rich in carbon and organic compounds, type C. This variety reflects the conditions and materials present in the protoplanetary disk at different distances from the Sun. Two asteroids stand out for their size and importance: Ceres and Vesta. Ceres, about 9 to 40 kilometers in diameter, is so large that it was reclassified as a dwarf planet by the International Astronomical Union. Observations from the Dawn spacecraft revealed that it has a surface covered with craters and bright spots composed of salts, possibly resulting from cryovolcanic activity, a type of volcanism where water and other cold liquids replace lava. There is also evidence that Ceres may harbor a subsurface reservoir of frozen water, which sparks astrobiological interest, since environments with liquid water can be candidates for microbial life. Vesta, about 525 kilometers in diameter, is one of the largest asteroids in the belt and has a surface with evidence of ancient volcanic activity. One of Vesta's most notable features is the gigantic crater at its south pole called Rhea Silvia, approximately 500 kilometers wide and 19 kilometers deep. The impact that formed this crater was so intense that it ejected fragments that eventually fell to Earth as meteorites, allowing scientists to study its composition directly. The asteroid belt is not merely a passive region of the solar system, it played a crucial role in Earth's history. During the late heavy bombardment, around 4 billion years ago, many of these bodies collided with the inner planets, contributing to the formation of craters and possibly delivering water and organic molecules to the primitive Earth. At the same time, these impacts represented significant threats, capable of triggering mass extinction events, such as the one that, 66 million years ago, wiped out much of life on Earth, including the dinosaurs. Exploration of the asteroid belt has increased in recent decades. Missions such as Dawn and OSIRIS-REx have shown that these bodies are true archives of the cosmic past, preserving chemical compositions and structures dating back to the earliest moments of the solar system. In addition to their scientific value, they also spark economic interest, as many contain precious metals and resources that could one day be exploited to support space activities. Despite its reputation as a danger zone for spacecraft, the distances between asteroids in the belt are so vast that spacecraft can cross it with relative safety. Even so, constant observation is essential, as some bodies can be deflected from their orbits and become near-Earth asteroids (NEAs), requiring monitoring to prevent possible collisions. The asteroid belt, therefore, is both a scientific and strategic frontier. It holds the raw material of planetary construction, bears witness to impacts that shaped worlds, and offers a glimpse into the distant past of the solar system. Exploring and understanding this region is both a study of our origins and a preparation for a future in which we may safely and productively interact with these rocky neighbors. The gas planets of the solar system, also known as giants, are massive worlds composed predominantly of hydrogen and helium, without a clearly defined solid surface. This category includes Jupiter and Saturn as true gas giants, and Uranus and Neptune as ice giants, due to their different composition. Although they share some basic characteristics, such as large dimensions, thick atmospheres, and numerous satellites, these planets present significant differences in their formation, structure, and atmospheric dynamics. The most striking feature of the gas giants is their size. Jupiter, the largest planet in the solar system, has a diameter of about 143,000 kilometers, while Saturn, the second largest, is approximately 120,000 kilometers across. Both are composed almost entirely of hydrogen and helium, gases that, under immense internal pressures, assume exotic states such as metallic hydrogen, capable of conducting electricity and generating extremely intense magnetic fields. Uranus and Neptune, on the other hand, although also containing hydrogen and helium, have a much greater proportion of heavier elements such as water, ammonia, and methane, which give them a denser and more differentiated internal composition. The formation of these planets is directly linked to their location in the solar system. In the outer region, where temperatures were low during the system's formation, ice and gases accumulated in large quantities, allowing the initial solid cores to grow rapidly and attract vast atmospheres. Jupiter and Saturn, being closer to the ice line, were able to accumulate much larger amounts of gas before the protoplanetary disk dissipated, resulting in colossal masses. Uranus and Neptune, farther away, formed in regions with lower gas density, which explains their less voluminous atmospheres and higher proportion of ice and heavier elements. All giants have dynamic and complex atmospheres, but their characteristics vary. Jupiter and Saturn display colorful bands, long-lasting storms, and intense wind systems that circle the planet at high speed. Jupiter's famous Great Red Spot, for example, is a gigantic storm that has lasted for at least 350 years. Uranus and Neptune, although visually more uniform, have extremely fast winds, in Neptune's case reaching over 2,000 km/h, and seasonal changes that are still not fully understood. Another key aspect is the presence of extensive systems of moons and rings. Saturn is famous for its bright and complex rings, composed mainly of ice and dust particles, but all giants possess ring systems, though less evident. Their moons, in turn, are fascinating worlds in their own right, with subsurface oceans, ice volcanoes, and their own atmospheres. Many of these moons, such as Europa and Enceladus, are among the main targets in the search for extraterrestrial life in the solar system. The magnetic fields of these planets are also remarkable. Jupiter has the most powerful magnetic field in the system, creating a gigantic magnetosphere that influences not only its moons, but also the surrounding space. Saturn's field is weaker, but still far stronger than Earth's. Uranus and Neptune have magnetic fields that are tilted and offset relative to the center, suggesting complex internal structures and unusual dynamics. From an exploration standpoint, gas and ice giants present both challenges and opportunities. The absence of a solid surface prevents conventional landings, but their moons and rings offer extremely rich study sites. Missions such as Voyager, Galileo, Cassini, and more recently Juno have revealed impressive details about these worlds, but there is still much to discover, especially about Uranus and Neptune, which have been visited only once by Voyager 2 in 1986 and 1989, respectively. In summary, the gas and ice planets are the titans of the solar system, shaping its gravitational dynamics, hosting potentially habitable lunar ecosystems, and offering clues about how planetary systems form in general. Understanding these giants means understanding the forces and processes that, since the solar system's infancy, have helped define the fate of all other worlds. Jupiter is the largest planet in the solar system and a true gravitational colossus, containing more mass than all the other planets combined. Located about 778 million kilometers from the Sun, it is a gas giant composed mainly of hydrogen and helium, with a dense core surrounded by layers of metallic and molecular hydrogen. Its formation dates back to the first millions of years of the solar system, when its solid core, possibly with 10 times the mass of Earth, rapidly accumulated gas before the protoplanetary disk dissipated. Due to its colossal mass, Jupiter played a crucial role in shaping the solar system's architecture, deflecting and capturing countless asteroids and comets, protecting the inner planets from catastrophic impacts, but also redirecting some toward the system's interior. Its atmosphere is one of the most dynamic and complex ever observed. It is composed mainly of hydrogen and helium, but also contains ammonia, methane, water vapor, and other compounds that, under different pressures and temperatures, create the characteristic colored bands of its visible surface. These bands result from jet streams that encircle the planet in opposite directions, forming bright zones, rich in frozen ammonia, and dark belts, deeper, warmer regions. Among the most impressive phenomena is the Great Red Spot, a gigantic anticyclonic storm that has lasted for at least 350 years and could swallow the entire Earth. This storm is fueled by the planet's intense internal energy, as it emits more heat than it receives from the Sun, an outcome of slow gravitational contraction and the movement of materials in its interior. Jupiter's magnetosphere is the largest continuous structure in the solar system, extending millions of kilometers into space. Its magnetic field, about 20,000 times stronger than Earth's, is generated by the movement of liquid metallic hydrogen in its interior. This magnetosphere traps charged particles and creates an extremely hostile environment for unshielded spacecraft, but also produces spectacular auroras at the planet's poles, far more energetic than those on Earth. Jupiter is also surrounded by a faint ring system, composed mainly of microscopic dust, likely originating from micrometeorite impacts on its inner moons. Although far less striking than Saturn's, these rings show that Jupiter is a complete system, with constant interactions between its components. Its collection of moons is equally remarkable, with over 90 known satellites. Among them, the four largest, known as the Galilean moons, discovered by Galileo Galilei in 1610, are fascinating worlds in their own right. Io is the most volcanically active body in the solar system, with hundreds of volcanoes erupting constantly due to tidal heating caused by Jupiter's gravity and that of the other moons. Europa has a cracked, icy surface beneath which is believed to lie a vast global ocean of liquid water. This environment, warmed by tidal forces, is one of the prime candidates in the search for life beyond Earth. Ganymede is the largest moon in the solar system, even bigger than Mercury, and has its own magnetic field, as well as evidence of subsurface oceans. Callisto, the outermost of the four, is covered in ancient craters and may have a deep salty ocean beneath its icy crust. The study of Jupiter and its moons is a scientific priority because it provides not only clues about the formation of gas giants, but also insights into potentially habitable environments beyond Earth. Missions such as Juno, currently orbiting the planet, and future probes like Europa Clipper and JUICE from the European Space Agency aim to explore both Jupiter's atmosphere and magnetic field, as well as the secrets hidden beneath the ice of its moons. Jupiter is, in essence, both a guardian and a natural laboratory. It directly influences the stability and evolution of the solar system and hosts some of the most promising worlds in the search for life. Observing and understanding this giant is to grasp an essential part of the history and future of our planetary system. Saturn is the second largest planet in the solar system, with a diameter of approximately 120,000 kilometers, and perhaps the most recognizable due to its spectacular ring system. Like Jupiter, it is a gas giant composed mainly of hydrogen and helium, but it has such low density that, theoretically, it could float in a sufficiently large ocean. Its formation took place at the same time as the other giant planets, about 4.5 billion years ago, rapidly accumulating gases from the protoplanetary disk thanks to its initial solid core and its distance from the frost line, where volatile compounds could condense more easily. Saturn's rings are its most striking feature and are made up of billions of particles of ice and dust, ranging from microscopic grains to mountain-sized blocks. These rings are not solid, but extremely thin structures, only a few dozen meters thick in some places, despite spanning hundreds of thousands of kilometers. They are organized into multiple sub-rings, separated by gaps created by gravitational interaction with Saturn's moons, known as shepherd moons, which help maintain the sharp edges and keep the particles in stable orbit. The origin of the rings is still debated. They may be remnants of a moon destroyed by collision, or Saturn's tidal forces, or leftover material from the planet's formation that never coalesced into a satellite. Saturn's atmosphere, though less colorful and contrasting than Jupiter's, is equally dynamic, with winds reaching over 1,800 km/h. Convection cells form cloud patterns and storms, including periodic events known as giant, long-lived storms, which can encircle the entire planet. Near the North Pole lies a unique atmospheric formation, a gigantic hexagon-shaped vortex, whose origin and stability continue to puzzle astronomers since its discovery by the Voyager probe. Saturn's magnetic field is strong, though less intense than Jupiter's, and creates a magnetosphere that shields its moons and rings from some cosmic and solar radiation. However, its moons make Saturn even more fascinating. It has more than 80 confirmed satellites, each with unique characteristics. Two stand out for their astrobiological potential. Titan, Saturn's largest moon, is bigger than the planet Mercury, and the only moon known to have a dense atmosphere, composed mainly of nitrogen with traces of methane. Its surface features lakes and seas of liquid methane and ethane, dunes and icy mountains. Beneath its frozen crust, there is believed to be a salty water ocean, making it an intriguing candidate in the search for microbial life. Enceladus, a relatively small moon, stunned the scientific world when the Cassini probe detected geysers ejecting jets of water vapor and ice particles from its south pole. These plumes indicate the presence of a global subsurface ocean in contact with mantle rocks, creating a potentially habitable environment with hydrothermal vents similar to those found on the ocean floors of Earth. Saturn's gravitational role in the solar system is equally significant. Its mass exerts strong influence over the asteroid belt and over comets passing through the outer regions, helping shape the orbital dynamics of numerous smaller bodies. Additionally, its interaction with Jupiter throughout history may have contributed to events such as the Late Heavy Bombardment, redistributing icy and rocky objects throughout the system. The exploration of Saturn and its moons has brought discoveries that changed humanity's view of icy worlds and their possibilities. The Cassini-Huygens mission, which orbited Saturn between 2004 and 2017, provided detailed images and data on the rings, atmosphere, and moons, including the Huygens probe's landing on Titan. This scientific legacy continues to inspire future missions, such as probes dedicated to exploring Enceladus and further studying its subsurface water. Saturn, with its majestic rings and a moon system that rivals any other in diversity, is a reminder that the solar system is not just a collection of isolated planets, but a complex network of gravitational, chemical, and geological interactions. It is both a visual icon of the cosmos and one of the richest natural laboratories for planetary science. Uranus is one of the most enigmatic planets in the solar system, classified as an ice giant, due to its composition rich in water, ammonia, and methane, mixed with hydrogen and helium. Located about 2.87 billion kilometers from the Sun, it completes an orbit in approximately 84 Earth years. What stands out most about Uranus, besides its blue-green coloration caused by the absorption of red light by the methane in its atmosphere, is its extreme axial tilt. Its axis is inclined about 98 degrees relative to its orbital plane. This means it essentially rolls sideways along its orbit, with its poles pointing almost directly at the Sun during certain phases. This unusual tilt was likely caused by a colossal collision with a planet-sized body in the early days of the solar system. The impact not only altered its rotation axis, but may have influenced its internal structure and the orientation of its magnetic field. The consequences of this tilt are dramatic. Each pole of Uranus experiences about 42 consecutive years of continuous sunlight, followed by 42 years of total darkness, creating extreme and unique seasonal patterns in the solar system. The atmosphere of Uranus is composed mainly of hydrogen and helium, with about 2% methane, along with small amounts of other hydrocarbons and possibly clouds of water and ammonia in deeper layers. Despite being farther from the Sun than Saturn, Uranus is one of the planets with the lowest internal energy source ever observed, emitting almost the same amount of energy it receives from the Sun. This remains a mystery to scientists, as other giant planets emit much more internal heat. Visually, Uranus appears calm, with few visible formations compared to Jupiter and Saturn. However, more detailed observations have revealed winds that can reach speeds over 900 km/h, as well as seasonal storms that intensify when the planet approaches its solstices. These changes suggest that its atmosphere can spend long periods in relative stability, followed by sudden bursts of climatic activity. Uranus is also surrounded by a system of narrow dark rings, composed mainly of ice particles coated with dark material, possibly carbon. These rings, discovered in 1977, are kept in place by the gravitational influence of small shepherd moons. In total, Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. Among the most notable are Miranda, a small but geologically intriguing moon, with giant cliffs and surfaces that appear to have been patched by multiple tectonic and cryovolcanic events. Ariel, which shows signs of past geological activity, such as valleys and smooth plains. Umbriel, the darkest of Uranus's major moons, possibly covered by carbon-rich material.
Stations,
Titania, and Oberon, the planet's largest moons, with ancient terrains filled with craters and large canyons. The magnetic field of Uranus is as peculiar as its tilt. It is highly inclined relative to the rotation axis and offset from the planet's center, creating an asymmetric and variable magnetosphere. This unique configuration is likely the result of a differentiated interior, where the ice and ammonia mantle influences the generation of the magnetic field differently than in gas giants. Uranus has been visited only once by a spacecraft, Voyager 2 in 1986, which provided most of the direct information we have about it. Since then, ground-based and space telescopes have been adding to our knowledge, but the planet still holds many secrets, including details about its internal structure, climate, and exact composition. From a scientific perspective, Uranus is a natural laboratory for studying how catastrophic events shape planetary evolution. Its extreme tilt, peculiar climate, and anomalous magnetic field make it a unique world in the solar system, challenging traditional models of planetary formation and dynamics. It is a reminder that even in a system we know relatively well, there are still mysteries that require exploration and new missions to be unraveled. Neptune, the eighth and most distant planet in the solar system, orbits about 4.5 billion kilometers from the Sun and completes a revolution every 165 Earth years. Classified as an ice giant, it shares with Uranus a composition dominated by water, ammonia, and methane, but stands out for its intense atmospheric activity and the fastest winds ever recorded on any planet in the solar system, reaching an astonishing 20,100 km/h. Its deep blue coloration is caused by the absorption of red light by the methane in its atmosphere, but the exact shade still intrigues scientists and may be related to other compounds and processes we do not fully understand. Neptune was the first planet to be discovered through mathematical calculations before being directly observed. In the mid-19th century, astronomers noticed that Uranus's orbit had small variations that could only be explained by the presence of another massive planet. Based on these anomalies, Neptune's position was independently predicted by Urbain Le Verrier and John Couch Adams, and the planet was first observed in 1846. This discovery marked a milestone in astronomy, proving the accuracy of Newton's gravitational laws. Neptune's atmosphere is composed mainly of hydrogen and helium, with about 1.5% methane and small amounts of other hydrocarbons. Despite receiving only a fraction of the solar energy that reaches Earth, Neptune displays surprising meteorological activity. Features such as the Great Dark Spot, observed by the Voyager 2 spacecraft in 1989, are giant storms comparable to Jupiter's Great Red Spot, but appear and disappear over much shorter timescales. Methane clouds, made of ice crystals, reflect sunlight and form bright patterns that move rapidly across the planet's deep blue background. Neptune also has a system of thin, dark rings composed of ice and dust particles coated with dark material, possibly carbon. Some of these rings have clumps known as arcs, which remain stable thanks to the gravitational influence of small nearby moons. The planet has at least 14 known moons, the largest and most fascinating of which is Triton. Triton is a unique and intriguing world. Unlike most of the large moons in the solar system, it orbits Neptune in a retrograde direction, meaning opposite to the planet's rotation. This indicates that Triton likely did not form alongside Neptune, but was captured by the planet's gravity, possibly having originally been an object from the Kuiper belt. This capture may have caused the collision and destruction of Neptune's original moons, generating impacts and internal heating within Triton. Triton's surface is a mixture of nitrogen ice, methane, and carbon monoxide, featuring smooth plains, rugged terrains, and active ice volcanoes, a phenomenon known as cryovolcanism. These volcanoes release plumes of gas and dust that can reach up to 8 kilometers in height, indicating that Triton is still geologically active, possibly due to tidal heating from its interaction with Neptune. The possibility of a subsurface ocean makes Triton a highly interesting target in the search for potentially habitable environments in the solar system. Neptune's magnetic field, like Uranus's, is strongly tilted and offset from the planet's center, creating a complex and asymmetric magnetosphere. This configuration influences its interaction with the solar wind and the distribution of charged particles around the planet and its moons. The only spacecraft visit to Neptune occurred in 1989, when Voyager 2 flew past the planet and Triton, sending back images and data that revolutionized our understanding of them. Since then, observations from space and ground-based telescopes have complemented our knowledge, but much remains to be discovered about Neptune's internal structure, atmospheric dynamics, and system of moons and rings. Neptune represents, in many ways, the final frontier of the planetary solar system. It is a reminder that even in the cold and distant reaches of our system, nature can create worlds full of activity, beauty, and mystery. And like Uranus, it reinforces the need for new missions to closely explore these ice giants and their surroundings, revealing secrets that have remained untouched since the formation of the solar system. Pluto, long considered the 9th planet of the solar system, has been classified as a dwarf planet by the International Astronomical Union since 2006, located at an average distance of 5.9 billion kilometers from the Sun. It orbits in the outer region known as the Kuiper belt, a vast ring of icy and rocky bodies that extends beyond Neptune's orbit. The Kuiper belt is considered the frozen equivalent of the asteroid belt, but much larger and with more diverse and distant objects, acting as a true reservoir of primordial material from the solar system. Pluto is a small world, with a diameter of about 2,577 kilometers, smaller than our Moon, yet surprisingly complex. Its surface displays an unexpected geological diversity, with vast plains of nitrogen ice, mountains made of water ice, and young regions free of craters that indicate recent geological activity. The most famous of these areas is Sputnik Planitia, a vast heart-shaped icy basin that appears to be constantly renewed by convection processes within the ice. This activity surprised scientists because Pluto is small and distant, receiving very little solar energy, which, in theory, should render it geologically dead. Pluto's atmosphere is extremely thin, composed mainly of nitrogen, with small amounts of methane and carbon monoxide. It is seasonal and can freeze and collapse onto the surface as Pluto moves away from the Sun in its 248-year elliptical orbit. Observations from the New Horizons a mission which flew by Pluto in 2015, revealed atmospheric haze layers that extend hundreds of kilometers above the surface, creating a striking blue spectacle when illuminated by the Sun. Pluto has 5 known moons. Charon. The largest is so big relative to Pluto, about half its size, that the two form a binary system, orbiting around a common point outside the surface of the dwarf planet. Charon also shows signs of past tectonic activity, with extensive canyons and icy regions. The other moons, Nix, Hydra, Kerberos, and Styx, are much smaller and irregular, probably formed from debris created by a major collision between Pluto and another Kuiper Belt object. The Kuiper Belt contains thousands of other objects known as trans-Neptunian objects, TNOs, including worlds such as Eris, Haumea, and Makemake, which also fall under the dwarf planet classification. These icy bodies vary greatly in size, shape, and composition, and many have their own moons. Some TNOs follow highly eccentric and inclined orbits, possibly influenced by the gravity of a hypothetical Pungii Planet 9, whose existence is still under investigation. Despite its reclassification, Pluto continues to play an important role in the study of the formation and evolution of the solar system. It is a clear example that size and position are not the only factors determining the complexity of a world. Its active geology, interactions with Charon, and seasonal atmosphere make Pluto as interesting as any planet. Exploration of the Kuiper Belt is only just beginning. After the New Horizons mission, which also flew past the object Arakoth, formerly called Ultima Thule, we know that many of these bodies preserve features virtually unchanged since the solar system's formation, acting as cosmic time capsules. Future missions could deepen our knowledge of this remote region, revealing more about the conditions that gave rise not only to Pluto, but to the entire set of icy worlds orbiting at the solar system's edge. Pluto and the Kuiper Belt remind us that the solar system is far more vast and diverse than the 8 classical planets. They represent a cold and mysterious frontier where small, distant worlds hold essential clues about the earliest days of our cosmic home. Comets are among the oldest and most mysterious travelers of the solar system, true time capsules that preserve the chemical composition of the protoplanetary disk from which all planets formed. These icy bodies, often called dirty snowballs, are primarily composed of water ice, carbon dioxide, carbon monoxide, methane, ammonia, and dust, along with mineral grains and complex organic compounds. When they remain in the cold, distant regions of the solar system, their appearance is modest, dark, irregular blocks. However, when a comet approaches the Sun, heating causes the sublimation of its ices, releasing gases and dust that form a bright coma and spectacular tails that can stretch for millions of kilometers. The basic structure of a comet consists of 3 main elements. Nucleus, solid, ranging from a few hundred meters to tens of kilometers in size, made up of a mixture of ice and rock. Coma, a temporary atmosphere formed when solar heat warms the nucleus, releasing gases and dust. Tails, usually 2. The dust tail, curved and yellowish, formed by particles reflecting sunlight, and the ion tail, bluish and straight, created by the interaction of ionized gas with the solar wind. Most comets originate from 2 distant regions, the Kuiper Belt, located beyond Neptune, and the Oort cloud, an immense hypothetical sphere of icy bodies that surrounds the entire solar system at distances between 2,000 and 100,000 astronomical units. Short-period comets, less than 200 years to complete an orbit, usually come from the Kuiper Belt, while long-period comets originate in the Oort cloud and can take millions of years to return. It is believed that gravitational perturbations caused by passing stars or galactic tides can dislodge these bodies, sending them toward the inner system. From a scientific perspective, comets are extremely important because they preserve the chemistry and structure of materials formed over 4-5 billion years ago. Studies indicate that they may have played a fundamental role in Earth's history, especially in delivering water and organic molecules during the late heavy bombardment. Samples analyzed by missions such as Rosetta, European Space Agency, and observations of comets like 67P Churyumov-Gerasimenko revealed the presence of amino acids, fundamental building blocks for life, suggesting that comets may have contributed to prebiotic chemistry on our planet. However, comets also pose potential threats. Their nuclei, though small, travel at high speeds, and an impact with Earth would release colossal energy, capable of causing destruction on a regional or even global scale, depending on the object's size. For this reason, comets that pass near Earth, called NEOCs, near-Earth object comets, are constantly monitored by telescopes and planetary defense programs. The observation of comets has fascinated humanity for millennia. Many cultures considered them omens, associating their appearance with important events or disasters. Today we know they are predictable natural phenomena, but they still inspire awe when they appear in the sky, visible to the naked eye. Some, like Halley's Comet, have become iconic, returning periodically and being recorded throughout history. Studying comets is not only a matter of scientific curiosity, but also a way to understand our own origins and prepare for possible future encounters. They are messengers from a remote past, coming from the most distant and cold regions, carrying valuable clues about how the solar system, and potentially life, came to be. The Oort cloud is one of the most mysterious and least understood regions of the solar system. It has never been directly observed, but it is strongly supported by mathematical evidence and by the orbital dynamics of long-period comets. Imagined as an immense sphere of icy bodies surrounding the entire solar system, the Oort cloud would extend from about 2,000 astronomical units, AU, from the Sun, 1 AU being the average distance between Earth and the Sun, to possibly 100,000 AU or more, reaching the space where the Sun's gravitational influence begins to merge with that of nearby stars and with galactic tides. This region is composed of trillions of icy objects, blocks of water ice, ammonia, methane, and other volatile compounds mixed with dust and rock. These bodies are remnants from the formation of the solar system, preserved in a virtually unaltered state for billions of years. It is believed that many of them originated in regions closer to the Sun, but were hurled outward by the gravitational action of the gas giants, especially Jupiter and Saturn, during the system's early formation phase. Once ejected to these immense distances, the objects were gravitationally captured and remained as a kind of frozen archive of cosmic history. The Oort cloud is generally divided into two parts: inner cloud, or Hill's cloud, denser and closer, with less inclined orbits; outer cloud, more spherical, with bodies distributed in all directions, forming a bubble that envelops the solar system. It is from this region that long-period comets are believed to originate, those that take thousands or even millions of years to complete an orbit. Small gravitational disturbances, such as the passage of nearby stars or the influence of galactic tides, can alter the orbits of these bodies and send them into the inner solar system. When this happens, they enter extremely elongated elliptical trajectories, becoming visible as they approach the Sun and develop their characteristic tails. From a scientific perspective, the Oort cloud is essential because it represents the gravitational boundaries of the solar system. It marks the frontier where the Sun's influence begins to give way to the external forces of the galaxy. This makes it not only a reservoir of icy bodies, but also a point of interaction between our system and the interstellar medium. It is possible that the Oort cloud contains captured interstellar objects, visitors from other systems trapped by solar gravity, and that, conversely, some of its bodies are eventually expelled, becoming interstellar travelers like the famous Oumuamua. The hypothesis of the Oort cloud was first proposed in 1950 by Dutch astronomer Jan Oort, who studied cometary orbits and concluded that they could not have originated in regions close to the Sun, as they would be destroyed or ejected quickly. Since then, computational models and indirect observations have reinforced the idea that this immense cloud exists even though we still lack direct images of its bodies. Directly exploring the Oort cloud is an almost unimaginable challenge for current technology. The distances are so vast that a probe would take thousands of years to reach it. However, studying comets believed to have come from this region already provides valuable information about their composition and about the conditions at the time of the solar system's formation. In essence, the Oort cloud is the invisible limit of our stellar home, a frozen wall that guards the oldest secrets of our cosmic neighborhood, and that from time to time sends bright messengers to remind us of the vastness and complexity of the universe we inhabit. The solar system, although it may seem isolated, is immersed in a dynamic environment within the galaxy. Its stability and current configuration do not depend solely on the sun's gravity, but also on external forces that act subtly or dramatically over billions of years. Among these forces are the gravitational influence of neighboring stars, galactic tides, and even the occasional passage of massive interstellar objects that can alter the orbits and destinies of bodies in the system. One of the regions most susceptible to these influences is the Oort cloud, located at the extreme limits of the solar system. Because its objects lie at immense distances from the sun, their gravitational bond is relatively weak, making them vulnerable to external disturbances. When a star passes relatively close to our system, on an astronomical scale, somewhere between 1 and 1 light-year, its gravity can alter the orbits of thousands of objects in that cloud, sending some into the inner solar system and others outward into interstellar space. An example of this is the case of the Schultz's star, which about 70,000 years ago crossed the edge of the Oort cloud. Although its mass and passing distance did not cause dramatic effects, it likely disturbed some orbits and may have sent comets into long-period trajectories. Such passages are not rare on cosmic timescales. It is estimated that every few million years, a star passes close enough to affect the dynamics of the solar system's outermost regions. Beyond individual stars, galactic tides, caused by the collective gravitational field of the Milky Way, also exert a constant influence. This effect is more noticeable in the outer regions of the system, where the sun's pull is weaker. Galactic tides can, over millions of years, slowly alter the orbits of the most distant objects, potentially ejecting some into interstellar space or pulling new visitors into the solar system. Another intriguing element is the hypothesis of the existence of Tanaig, massive stellar intruders, or even a large undiscovered planet, the so-called Planet 9, whose gravity could be perceptibly affecting the orbits of trans-Neptunian objects. Some astronomers suggest that anomalies observed in the orbits of certain bodies in the Kuiper Belt could be explained by a planet several times the mass of Earth, located far beyond Pluto, or even by a brown dwarf star that might have passed through the system in the distant past. It is also important to consider that the Sun's own orbit around the center of the galaxy, completed every 225 to 250 million years, takes the solar system through different regions of interstellar space. Some of these regions may have higher stellar or gas densities, increasing the likelihood of gravitational interactions and events such as nearby supernovae, which could indirectly affect Earth's atmosphere and biosphere. These external influences not only reshape the population of comets and asteroids, but also have the potential to trigger profound changes in the history of Earth and other planets. There are theories suggesting that certain mass extinction events may have been preceded by increases in the rate of impacts, possibly related to external gravitational disturbances that sent swarms of comets toward the inner regions of the solar system. The study of the gravitational influence of other celestial bodies is therefore a key piece in understanding the long-term evolution of our planetary system. It reminds us that even at great distances, subtle forces can accumulate significant effects over millions of years, and that the solar system is only a small gear in a much larger cosmic machine, governed by interactions that span almost unimaginable scales of time and space. The solar system, although often imagined as static, is in constant motion within the Milky Way. Just as the Earth orbits the Sun and the Moon orbits the Earth, our entire planetary system orbits the center of the galaxy, completing a full revolution every 225 to 250 million Earth years, a period known as the Kaizen Galactic Year. During this journey, The solar system travels at an average speed of approximately 828,000 km/h, crossing different regions of the galaxy and experiencing subtle yet significant variations in the conditions of interstellar space. The Milky Way is a barred spiral galaxy, with arms formed by concentrations of gas, dust, and stars. The Sun and its planets are located in the Orion Arm, a small subdivision between two larger arms, Sagittarius and Perseus. As it orbits the galactic center, the solar system does not follow a perfectly circular path, but a slightly elliptical and undulating one, periodically crossing the galactic plane. This vertical oscillation occurs approximately every 30 million years and may influence the stability of the Oort cloud, potentially increasing the frequency with which long-period comets are sent into the inner system. Throughout this cosmic journey, the solar system passes through regions with varying stellar densities and concentrations of interstellar dust. In denser areas, the increased cosmic radiation and the gravitational pull of neighboring stars can alter the dynamics of the most distant bodies, such as comets and trans-Neptunian objects. There are also hypotheses linking passages through such regions to mass extinction events on Earth, although these connections remain the subject of scientific debate. Another important aspect is that the movement of the solar system exposes it on very long timescales to possible close encounters with other stars. These encounters may have minimal effects or, in rarer cases, cause significant disturbances to the Oort cloud or even to the orbits of dwarf planets. Furthermore, during its galactic orbit, the system may cross spiral arms, regions richer in young massive stars where the likelihood of nearby supernovae is greater. These stellar explosions can influence Earth's atmosphere and even contribute to climatic and evolutionary changes. The Sun itself does not travel alone. It is accompanied by a vast entourage of planets, moons, asteroids, comets, and dust, all gravitationally bound and moving together as a cohesive system. However, each of these components follows its own orbit around the Sun, creating an intricate cosmic ballet that takes place simultaneously with the motion of the whole through galactic space. The awareness that the solar system is in constant motion reinforces the idea that we live in a dynamic universe. Throughout Earth's geological history, our cosmic address has been in different parts of the galaxy, each with its own characteristics and potential influences. This perspective also enhances the importance of studying astrobiology and planetary evolution, as conditions in interstellar space may play a greater role than we imagine in the development and preservation of life. Ultimately, the movement of the solar system around the Milky Way is a reminder that our planet and all its inhabitants are part of a colossal journey, one that began even before the formation of Earth and will continue for billions of years as the galaxy evolves and transforms. It is a silent voyage, yet one that subtly shapes the destiny of everything we know. A planet's climate is the result of a delicate balance between internal factors such as geological activity, atmospheric composition, and the distribution of continental masses, and external factors such as the radiation received from the central star, gravitational interactions with other bodies, and cosmic impacts. In the solar system, each planet and moon presents a unique climate history, shaped by these forces over billions of years, and understanding these changes is essential not only to grasp the evolution of distant worlds, but also the past and future of Earth. One of the most influential internal factors is geological activity. The presence of volcanism, tectonism, and cryovolcanism can significantly alter a planet's atmosphere, releasing gases that affect the greenhouse effect or injecting particles that reflect sunlight. On Earth, massive volcanic eruptions, such as those that occurred in the Deccan Traps and Siberian Traps, had a profound impact on climate, causing periods of global cooling or warming and even contributing to mass extinction events. On Venus, volcanism may have resurfaced the planet and maintained a dense carbon dioxide atmosphere, leading to a runaway greenhouse effect. On Enceladus and Europa, cryovolcanism sustains subsurface oceans that remain warm and chemically active. Atmospheric composition is another critical regulator. Dense atmospheres like those of Venus and Titan can retain heat for long periods, while thin atmospheres like that of Mars lose heat quickly, resulting in large temperature variations. The presence of greenhouse gases such as carbon dioxide, methane, and water vapor, can significantly warm a planet's surface, while suspended particles, such as dust and aerosols, can reflect solar radiation and promote cooling. Changes in atmospheric composition can occur gradually through natural processes or abruptly due to events such as asteroid impacts. Among the external factors, variation in solar luminosity plays a central role. The sun is not a constant source of energy. Its luminosity changes on timescales, ranging from 11-year cycles to variations spanning billions of years. In the distant past, the sun was about 30% less luminous than it is today, creating the so-called faint young sun paradox, which suggests that other mechanisms, such as higher concentrations of greenhouse gases, helped keep Earth warm. Small changes in a planet's orbit or axial tilt, known as Milankovitch cycles, in Earth's case, can also trigger ice ages or interglacial periods. Gravitational interactions with other bodies can affect both the orbit and rotation of a planet, altering its climate over the long term. Mars, for example, without a large moon like ours to stabilize its axis, experiences chaotic variations in axial tilt, causing intense climate changes over millions of years. In addition, the presence of a nearby giant planet can influence the flow of asteroids and comets into the inner regions, increasing the frequency of impacts. Cosmic impacts are another external factor capable of causing abrupt climate change. The Chicxulub event, 66 million years ago, threw so much dust and aerosols into Earth's atmosphere that it blocked sunlight for months or years, triggering an impact winter that led to the extinction of much of life on Earth, including non-avian dinosaurs. On other worlds, impacts can have similar effects, or even completely reshape the surface and atmosphere. The shut galactic movements of the solar system can also indirectly influence planetary climates. As it crosses regions of the galaxy richer in dust or closer to massive stars, the radiation received and the frequency of cosmic events, such as supernovae, can temporarily change climate conditions. Studying planetary climate change gives us insight into how different combinations of factors can create extreme or stable environments. This understanding is vital to predict Earth's fate and assess the habitability of exoplanets. In the end, each planet is the result of a delicate interplay between internal and external forces, and climate is one of the clearest records of this cosmic dance over time. The exploration of the solar system is one of humanity's greatest achievements, an endeavor that has transformed our understanding of space and revealed surprising details about worlds that were once only points of light in the sky. From the beginning of the space age in the 1950s to the most advanced missions of the 21st century, each step taken beyond Earth has expanded not only our scientific knowledge, but also our ability to imagine and plan a future among the stars. The starting milestone of this journey was the Soviet lunar tour mission, which in 1959 became the first human-made object to reach the surface of the Moon. Just a few years later, in 1969, the American Apollo 11 mission took the first humans to walk on the lunar surface, a feat that remains one of the most iconic moments in history. The Apollo missions not only collected valuable samples, but also installed instruments that provided data on the Moon's composition and seismic activity. The next step was to extend exploration to other planets and moons. The Mariner probes paved the way for the study of Mercury, Venus, and Mars, while the Pioneers and Voyager missions expanded the limits of our presence, visiting Jupiter, Saturn, Uranus, and Neptune, and sending back data that are still being analyzed today. Voyager 1, launched in 1977, is currently the most distant object from Earth, traveling in interstellar space and carrying the famous Golden Record with messages and sounds from humanity. Missions dedicated to specific planets have revolutionized our knowledge. The Galileo probe studied Jupiter and its moons, revealing subsurface oceans on Europa. Cassini-Huygens explored Saturn and Titan, discovering ice plumes on Enceladus and liquid methane lakes on Titan. Juno is investigating Jupiter's interior and magnetic field, while New Horizons gave us our first detailed glimpse of Pluto and the Kuiper Belt object Arakoth. Mars, in particular, has been the target of intense exploration. Missions such as Spirit, Opportunity, Curiosity, and Perseverance have revealed evidence of past water, habitable conditions, and even signs of organic molecules. Orbiters like the Mars Reconnaissance Orbiter and Maven complement these studies by monitoring the planet's atmosphere and surface. Beyond planets, asteroids and comets have also been explored up close. The Daunt probe visited Vesta and Ceres in the asteroid belt, while the OSIRIS-REx brought samples from the asteroid Bennu back to Earth. The Rosetta mission orbited and landed on comet 67P Churyumov-Gerasimenko, revealing details of its structure and composition and confirming the presence of complex organic molecules. Another important milestone is the exploration of the outer solar system and its boundaries. The Voyager and New Horizons probes continue to send data about the heliosphere and the interstellar environment, helping us understand how the solar wind interacts with the galaxy. Future missions such as Europa Clipper and JUICE, Jupiter Icy Moons Explorer, will investigate icy worlds that may harbor life in subsurface oceans. The impact of space exploration goes beyond science. It influences technology, culture, and even global politics. Every image captured, every discovery made, reinforces the idea that the solar system is a vast, diverse, and dynamic place full of unique worlds and fascinating phenomena. At the same time, these missions show that, although we have taken impressive steps, we have still explored only a tiny fraction of what exists around us. Ultimately, the exploration of the solar system is a natural extension of human curiosity. It represents not only the desire to know, but also the preparation for a future in which we may live, work, and perhaps even thrive on other worlds. With new missions planned for the coming decades, each discovery brings us a little closer to understanding the entirety of our cosmic home. Despite decades of exploration and detailed observations, the solar system still holds countless secrets that intrigue scientists and defy explanations. These mysteries range from subtle anomalies in the orbits of certain bodies to geological and atmospheric features that seem incompatible with what we know about physics and planetary formation. They serve as a reminder that, as far as we have advanced, we are still far from fully understanding the complexity of our cosmic home. One of the most debated enigmas today is the possible existence of Planet 9, a massive body far beyond Pluto, whose presence is suggested by unusual patterns in the orbits of some trans-Neptunian objects. These objects exhibit alignments and inclinations that, according to some models, would be difficult to explain without the gravitational influence of a planet several times the mass of Earth. Despite intense searches, Planet 9 has yet to be directly detected, raising alternative hypotheses, such as the combined influence of several smaller objects or even past interactions with nearby stars. Another mystery involves gravitational anomalies observed in space probes, known as the Pioneer anomalies. These minimal variations, recorded in the trajectories of the Pioneer 10 and 11 spacecraft, sparked debates over possible adjustments needed in gravitational physics. Although part of the phenomenon has been attributed to the thermal radiation emitted by the probes themselves, it illustrates how precise measurements can reveal unexpected discrepancies. In geological terms, some bodies show signs of recent internal activity that should not exist according to our models. Pluto, for example, has regions almost free of craters, indicating surface renewal on relatively short time scales despite its small size and low internal energy. On Enceladus and Europa, plumes of water vapor emerge from fractures in the ice, fueled by subsurface oceans warmed by tidal heating. Although tidal heating explains part of this activity, the intensity and persistence of these processes still raise questions about additional energy sources. The atmosphere of Titan, Saturn's largest moon, is another enigma. Rich in nitrogen and methane, it should have lost this gas over billions of years, yet methane remains abundant. This suggests the existence of internal processes, possibly cryovolcanism, replenishing the atmosphere, but the details of this cycle remain unclear. Climatic phenomena also puzzle scientists. On Neptune and Saturn, giant storms appear suddenly, while on Venus the so-called superrotation of the atmosphere, which circles the planet in just 4 days, much faster than its rotation, remains without a definitive explanation. Jupiter, meanwhile, shows variations in the Great Red Spot, whose origin and potential disappearance are closely monitored. In addition, The detection of unexpected compounds on certain bodies raises questions about poorly understood chemical processes. One example is the possible presence of urphosphenon on Venus, observed by telescopes in 2020. Although this gas can be produced by non-biological processes, on Earth it is mainly associated with microbial activity, reigniting debates about the possibility of life in extreme environments. The study of comets also reveals mysteries. The Rosetta mission found complex organic molecules on Comet 67P Churyumov-Gerasimenko, but also discovered oxygen molecule levels that do not match the chemistry expected for such ancient bodies. This suggests that some fundamental processes in the formation of the solar system are still not fully understood. These enigmas are more than curiosities. They point to gaps in our knowledge and encourage new missions and observations. Every mystery solved has the potential not only to explain a specific phenomenon, but also to reshape entire concepts in planetary science. It is precisely this combination of discoveries and unanswered questions that keeps the exploration of the solar system alive, reminding us that the unknown is still vast, and that the next great revelation may be just a telescope or probe away. The Sun, like all stars, has a life cycle determined by the amount of nuclear fuel available in its core. It is currently about halfway through its most stable phase, known as the South main sequence, during which it converts hydrogen into helium through nuclear fusion. This phase should last for about another 5 billion years, but over time, subtle changes in its brightness and structure will profoundly affect all the planets in the solar system. As the hydrogen in the core is consumed, the rate of fusion decreases, causing gravity to slowly compress the core and increase its internal temperature. This heating causes the Sun's outer layers to expand and its luminosity to gradually increase. Even before it becomes a red giant, this rise in solar brightness will have drastic consequences for Earth. In about 1 billion years, the increase in energy will be enough to cause the evaporation of the oceans and the collapse of the biosphere, making the planet inhospitable to life as we know it. When the hydrogen fuel in the core is depleted, the Sun will enter a phase of instability. Its outer layers will expand enormously, and it will transform into a red giant, potentially reaching a radius that engulfs the current orbits of Mercury and Venus, and perhaps even Earth, depending on the mass loss that occurs. During this phase, the Sun will lose a significant portion of its mass through intense stellar winds, reducing its gravity and causing the orbits of the outer planets to expand. This expansion will radically change the solar system. Mercury and Venus will certainly be swallowed. Earth, if it escapes direct engulfment, will be so close to the Sun's incandescent surface that its rocks will melt, its atmosphere will be stripped away, and any trace of life will vanish. Mars might temporarily become milder, but only for a short period before it too becomes uninhabitable. The icy moons of Jupiter and Saturn might have their subsurface oceans exposed and temporarily warmed, but in the end, the entire inner system will be sterile. In the core of the red giant, the increase in temperature will allow helium to fuse into carbon and oxygen. This phase, however, will be brief compared to the main sequence. After a few million years, the helium fuel will also be exhausted, and the Sun will no longer have enough pressure to support its outer layers, which will be expelled into space, forming a planetary nebula, a luminous shell of gas and dust that will shine for tens of thousands of years. The remaining core will become a white dwarf, an extremely dense object about the size of Earth but with half of the Sun's original mass. This white dwarf will be composed mainly of carbon and oxygen and will emit residual heat for billions of years, slowly cooling until it becomes a hypothetical black dwarf, invisible and frozen. The future of the Sun is therefore both majestic and destructive. It will transition from a stable, life-giving star to a world-devouring red giant, and finally to a silent white dwarf, marking the end of the stellar life cycle. For planets and moons, this fate will be relentless, but for science, it is an opportunity to observe and predict what may happen in other planetary systems. Studying stars at different stages of life allows us to see our own future more clearly, and to understand that, even for a system as familiar as ours, change is inevitable. The future of Earth is directly tied to the fate of the Sun, but its trajectory toward uninhabitability begins long before our star's final stage. Even while remaining in the main sequence, the sun will gradually increase its brightness and temperature, irreversibly altering the planet's climate and geology. This slow but constant change will trigger a chain of events that, over billions of years, will transform Earth into a world radically different from the one we know today. In about 500 million years, the increase in solar luminosity will disrupt Earth's carbon cycle. Greater water evaporation will intensify the chemical weathering of rocks, which in turn will remove carbon dioxide from the atmosphere. This process, which today helps maintain the planet's thermal balance, will eventually reduce CO2 levels to a critical point, making photosynthesis impossible for plants that rely on the C3 process, which includes most current plant species. With the death of these plants, the global food chain will begin to collapse. In approximately 1 billion years, the continued increase in energy received will cause the oceans to begin evaporating on a large scale. Water vapor, a potent greenhouse gas, will accumulate in the atmosphere, amplifying the warming and accelerating the loss of water to space. Earth will enter a runaway greenhouse effect, similar to what occurs on Venus, raising temperatures to levels incompatible with any form of complex life. As the planet approaches the sun's red giant phase, around 5 billion years in the future, the surface will become an ocean of molten rock. If it is not directly engulfed by the sun, Earth will be left as a sterile rocky core without an atmosphere or water, orbiting an unstable star. The mantle and crust will be deeply altered, and any trace of ancient mountains, oceans, or cities will be erased. Even in this extreme scenario, some underground regions may retain residual heat for a time, but without the protection of an atmosphere and with absurdly high surface temperatures, any remaining microbial life will be extinguished. Earth's magnetic field will also weaken over billions of years, leaving the planet more vulnerable to cosmic radiation and the solar wind. After the sun's outer layers are expelled and a planetary nebula is formed, Earth, if it still exists physically, will orbit a white dwarf. The light and heat from this new star will be insufficient to sustain any kind of atmosphere or moderate temperature. The planet will become a dark, frozen body, with its surface covered in crystallized minerals and scars from billions of years of impacts and transformations. This fate, as inevitable as it may be, also offers valuable lessons. It reminds us that habitable worlds are temporary on a cosmic scale, and that life, if it wishes to endure, must adapt or migrate. Modern space science already considers that the long-term survival of Earth's life will depend on our ability to colonize other planets or stellar systems before the sun enters its terminal phase. The end of Earth, therefore, is not just a story of loss and destruction, but also a call for humanity to prepare to move beyond its cosmic cradle. The final fate of the solar system is one of the most fascinating and inevitable topics in astrophysics, as it involves not only the collapse of our sun, but also the impact of this transformation on all the bodies that currently orbit under its gravity. When the sun exhausts its fuel and goes through the red giant and planetary nebula phases, the gravitational balance that keeps the planets in their orbits will be profoundly altered. From that moment on, the dynamics of the system will change irreversibly. The first major consequence will be the yin-ti loss of solar mass. During the red giant phase, the sun will expel enormous amounts of material into space in the form of intense stellar winds. This loss could reach up to half of its current mass. As a result, the gravity exerted by the sun will decrease, causing the orbits of the remaining planets to expand. More distant objects, such as Neptune, Pluto, and bodies in the Kuiper belt, could be displaced into unstable orbits, or even completely ejected from the solar system, becoming rogue planets, wandering alone through interstellar space. After the expulsion of its outer layers, the sun's core will become an extremely dense white dwarf, roughly the size of Earth. This dead star will no longer have nuclear fusion, emitting only the residual heat it has accumulated. Over time, it will cool slowly, becoming increasingly darker. Without a significant energy source, the remaining planets and moons will be plunged into extreme cold, their surfaces frozen, and their atmospheres, if still present, freezing and precipitating as snow made of gases. On much longer timescales, trillions of years, even the white dwarf will fade from view, becoming a hypothetical black dwarf. This virtually invisible object will still exert gravity, but will emit no light or heat. At this stage, the solar system will no longer exist as a living, active system, becoming only a collection of frozen bodies orbiting a dead core. Some theories suggest that the remaining orbital stability will be temporary. The gravitational influence of nearby stars, galactic tides, or encounters with massive objects could gradually disturb and dismantle the system. Planets, moons, and asteroids could slowly be expelled from their orbits until nothing remains bound to the white dwarf. There are also models that consider a more dramatic scenario: collisions with other stars or the capture of planets by nearby systems, events possible on galactic timescales. In this context, fragments of the ancient solar system could continue to exist as part of different systems, spreading across the Milky Way as remnants of a distant past. The fate of the solar system is closely linked to the fundamental laws of physics and the stellar life cycle. It will not be destroyed by a sudden violent event like a supernova, but rather by a gradual process of energy dissipation and weakening gravity. This transition from heat and light to cold and darkness is inevitable, but also natural in the cosmic context. Understanding this process helps us realize that our home in the universe is temporary, and that for life to continue, it will be necessary to expand our presence beyond the boundaries of the solar system before it becomes just a cold, silent memory in the history of the galaxy. The disappearance of the Sun as an active star represents not only the end of a stellar cycle, but also a definitive sentence for all forms of life that depend on its energy. If humanity or its descendants still exist in that distant future, survival will require a level of planning and adaptation far beyond any challenge ever faced. With the gradual increase in solar luminosity even before the red giant phase, conditions on Earth will become increasingly hostile, forcing life to either adapt or migrate. In the short term, in astronomical terms, the first major consequence will be the collapse of the biosphere. As average temperatures rise, ocean evaporation increases, and carbon dioxide is lost from the atmosphere. Photosynthesis will go into decline, triggering the collapse of food chains. Animals and plants will disappear in a sequence of extinctions, and the last habitable niches will be restricted to underground areas or deep underwater regions, until even those can no longer sustain life. For humanity, if it still exists, the only viable path will be the development of technologies capable of creating artificial ecosystems completely independent from the external environment. This includes enclosed habitats, food production in controlled conditions, and energy generation from sources not directly dependent on sunlight. However, even these refugees would have a limited lifespan, as environmental deterioration and advancing climate change would make it increasingly difficult to maintain stability. As the red giant phase approaches, survival will require abandoning Earth. This transition would involve developing enormous fleets of ships capable of transporting entire populations to other worlds, or possibly to younger star systems. The engineering required for such a feat would include not only interstellar travel, but also the construction of permanent space colonies capable of operating for thousands of years. Some theories suggest that advanced civilizations could even move entire planets into more distant orbits using gravitational propulsion techniques with asteroids or massive spacecraft. While this idea sounds like science fiction today, it is mathematically possible and could, in theory, extend the habitability of worlds like Earth or Mars for millions of additional years. When the Sun finally becomes a white dwarf, any survival within the solar system will depend on alternative energy sources. Colonies on icy moons or artificial habitats would need to rely on fusion reactors, geothermal energy, or other advanced forms of technology. However, over very long timescales, even these solutions would become unfeasible, forcing humanity, or what remains of it, to seek new homes in other systems. The psychological and cultural impact of such an exodus would be immense. The Sun is not just our source of life. It is part of Earth's identity, of the natural cycle, and even of the mythology of various cultures. Living without it would mean breaking a bond that has shaped our evolution for billions of years. Humanity, in this scenario, would become a truly interstellar species, carrying memories and records of a planet that no longer exists, preserving its history as an ancestral legacy. Thus, the end of the Sun does not merely represent the physical closure of a stellar system, but also the greatest test of resilience and ingenuity any civilization could face. The difference between total extinction and the continuation of life will lie in our ability to understand, anticipate, and act in the face of the inevitable. The trajectory of the solar system is a cosmic narrative that spans more than 4.5 billion years, marked by violent events, periods of stability, and profound transformations that shaped every planet, moon, and celestial body. From the initial collapse of a molecular cloud to predictions about its distant future, this story is both a testament to the power of the laws of physics and a reminder of the fragility of the conditions that allow life to exist. Its origin dates back to the gravitational collapse of an immense cloud of interstellar gas and dust, possibly triggered by the shockwave of a nearby supernova. From this collapse, a rotating protoplanetary disk formed, in which matter began to clump together, giving birth to the Sun at the center and to the planets at different distance zones. The heat and radiation from the young Sun shaped the distribution of matter, separating rocky worlds in the inner regions from gas and ice giants in the more distant areas. The first hundreds of millions of years were a time of chaos, with frequent collisions that sculpted landscapes, formed moons, and created craters that remain as scars to this day. It was in this scenario that Earth gained its moon, probably from a massive collision with a Mars-sized body. Water, essential for life, arrived largely through comets and asteroids, while chemical reactions on the planet's surface and interior prepared the stage for the emergence of the first organisms. As the ages passed, the solar system entered a more stable state, but it was never completely unchanging. Planets and moons continued to evolve, atmospheres formed and dissipated, and gravitational interactions altered trajectories and orbits. Some worlds maintained conditions favorable to the presence of liquid water, while others became barren deserts or icy spheres. Modern space missions such as the Voyager, Cassini, and New Horizons probes have expanded our understanding, revealing that even in the frozen depths, oceans and active geological processes may exist. The present is an era of observation and discovery. We are mapping Mars's surface in high resolution, analyzing ice plumes on distant moons, and detecting orbital anomalies that may indicate the presence of new, unidentified bodies. At the same time, we are observing other planetary systems to understand how ours fits into the broader context of the galaxy. The future, however, is inevitably governed by the Sun's evolution. The gradual increase in its luminosity will transform Earth and other inner worlds into hostile environments, culminating in the red giant phase and the formation of a silent white dwarf. With this, the solar system will cease to be the vibrant cradle of life and will become a scattered set of cold bodies in altered orbits. This timeline, from birth to death, is not just an astronomical record, but also a reminder that life and planetary stability are temporary. Understanding this history offers us not only knowledge but also perspective. We live in a brief and privileged moment, on a planet that still maintains ideal conditions for life. Preserving this balance and planning beyond it may be the difference between disappearing with the natural fate of our world or transcending the limits of our system of origin. The solar system is, therefore, more than a collection of planets and moons orbiting a star. It is a story in constant transformation, a natural laboratory for science, and a home whose importance goes far beyond astronomy. It is a reminder that in the midst of the vast and impersonal universe, we have found a unique place, and that it is up to us to decide what we will do with the time granted to us under the sun's light. If you have made it this far in our journey through the solar system, subscribe to the channel to keep following our scientific documentaries. Leave your like, share this video with those who also love science. Which part of this story impressed you the most? And tell me from which city you are watching. I would love to know how far this journey has reached. Your participation is what keeps this project alive and motivates us to bring you more and more content like this.